Information systems exist to share data across networks, yet security engineering requires us to strictly restrict that exact capability. For decades, the industry managed this paradox using a perimeter model. Organizations built a hard, defensive outer shell around their network, assuming that any device or user operating within the soft, trusted interior was safe. This internal security posture relied heavily on the phrase "trust but verify," a concept popularized by former President Ronald Reagan to describe the diplomatic relations and arms control agreements with the Soviet Union. Applying this geopolitical philosophy to digital systems is a fatal architectural flaw. The assumption that a safe inside can be separated from a dangerous outside by a single perimeter wall is no longer viable. The corporate perimeter has been erased. Employees carry mobile devices into private networks, access cloud computing services, and connect to edge computing sensors that blur the line of where the internal network actually ends. When that perimeter is inevitably breached, the trust but verify model backfires. An external attacker who gains entry is immediately granted the freedom to perform lateral movement across those implicitly trusted internal systems. Modern security architecture must abandon the illusion of implicit trust entirely. System designers must assume hostility exists at every node, internal or external, before a single packet of data is transmitted. Controlling access in a secure system relies on two entities. The active entity requesting access is the subject, and the passive resource accessed is the object. These entity designations are highly fluid in practice. They are specific to individual access requests, rather than permanent roles assigned to specific machines. This table shows how roles shift during sequential requests. When process A asks for data from process B, B acts as the passive object. To satisfy that request, B must ask for data from process C, immediately becoming the active subject in the second transaction. This diagram illustrates transitive trust. If entity A trusts entity B and B trusts C, A inherits the trust of C. This creates a severe security vulnerability, allowing an active subject to completely bypass established limitations between itself and a restricted object. Consider an organization that blocks local network access to a specific social media website to enforce worker productivity. If a worker connects to a virtual private network, or VPN, they establish a new trusted relationship between their machine and the proxy server. Because the VPN service has the ability to reach the blocked social media site, the worker can access the restricted site through the VPN. The proxy serves as the transitive vector that defeats the network restriction. Transitive trust exploits are inherent to the logic of networking itself. Building a stronger perimeter wall is architecturally useless against mathematical properties circumventing direct barriers. System design is divided by two differing philosophies: open systems and closed systems. Open systems are built using agreed-upon industry standards. They rely heavily on application programming interfaces, or APIs, defined sets of rules that allow computing elements to interact directly and share information. The business advantage of open systems is massive interoperability. Administrators can easily integrate a Windows server, a Linux machine, and a macOS device on the same local area network. This interoperability extracts an immediate security cost. Standardized communication components create highly predictable entry points, giving attackers a massive shared body of exploitation knowledge to draw from. Closed systems take the opposite approach. By relying on proprietary hardware and software and rejecting industry standards, they force attackers to possess in-depth knowledge of the target and craft unique, custom exploits. Regardless of the system type, vendors optimize their software for deployment, leading to a vulnerability known as the tyranny of the default. Default configurations are rarely selected to maximize security. They are chosen by the vendor to minimize installation friction and reduce the load on their technical support services. System administrators face a strict architectural mandate. They must assume the default settings of any product are the worst possible options for their organization. Administrators must implement strict restrictive defaults, intentionally deploying systems in a limited, hardened capacity where only the necessary features are enabled. This practice connects to broader computing minimalism, governed by principles like KISS, keep it simple and small, and the principle of Yagni, you aren't going to need it, which dictates that developers should only write code and capabilities when they are absolutely necessary. In architectural engineering, complexity is the enemy. Every unused feature, open API, and default settings left active is simply an unmonitored attack vector. System failure in engineering is entirely deterministic. Systems do not crash randomly. They fail in specific directions engineered by their designers. The first line of defense is programmatic error handling. Programmers use logical blocks like try-catch statements, code designed to anticipate an error and execute an alternative action before the program terminates. The ideal outcome is a fail-soft state. This allows a system to absorb the failure of a single component while continuing partial operations. When a fail-soft state is impossible, the system will fail completely. The architect must decide in advance what the system will sacrifice during that total failure. This table maps out how systems handle these total failures. As shown in the top 2 rows, if a system affects the physical environment, it must prioritize human life above all else. This physical priority is called fail-safe or fail-open. An electronic door lock engineered to fail safe will automatically unlock during a fire, sacrificing the security of the building to allow people to escape. The bottom 2 rows show the priorities for strictly digital environments. Here, the system must prioritize the CIA triad, specifically protecting the confidentiality and integrity of the digital assets. This digital priority is called fail-secure or fail-closed. The system intentionally sacrifices its own availability to prevent unauthorized access or data corruption. When a firewall fails closed, it severs all communications, rather than passing unfiltered traffic. When an operating system encounters a severe memory violation, it triggers a blue screen of death, terminating all executions to protect the system architecture. Designing how a system breaks is just as vital as designing how it operates. Dropping digital shields to preserve uptime is a catastrophic architectural failure. The perimeter model cannot survive modern networking. Transitive trust is mathematically exploitable, open APIs are inherently vulnerable, and digital systems must be engineered to fail closed. The solution is Zero Trust, formalized in NIST Special Publication 800-207. It mandates that no entity, whether internal or external, is automatically trusted. Zero Trust operates on an assume breach mentality. The architect builds the network under the assumption that malicious actors are already inside every system. The primary operational mechanism of this model is microsegmentation. Microsegmentation divides the internal network into subzones as small as a single endpoint device. All traffic flowing between these isolated zones is aggressively filtered. The transaction rules are absolute. Every single request between devices must be authenticated, authorized, and encrypted before access is granted. Zero Trust architecture relies heavily on visibility. Because threats and connection characteristics change, the system only functions if continuous, real-time monitoring is maintained to vet user activities. For high-value targets where filtered interaction poses too much risk, the ultimate extreme of isolation is required: the air gap. An air gap ensures total physical network isolation, removing all cabled and wireless links. To enforce this, facilities may use a Faraday cage, an enclosure used to block electromagnetic fields, preventing any wireless bridging. True security architecture relies on engineering a granular, assumption-free environment where every interaction is interrogated at every step.